top of the morning to you. Just a reminder that all I'm asking you guys to do, I'm trying to make it as easy as possible, is just watch the videos. And the second exam is going to be, we're going to do a review for it, but it's going to be very straightforward questions, probably more questions than on your first test, because they're going to be more straightforward questions, okay? And it's going to be covering 2 exams, so there's going to be a lot of questions there. So stay up on the lectures, guys. My fear, and I know law of large numbers, but my fear is that you're going to wait until the last night and try to watch all the videos. And so little bites of the apple, man. It's not a lot to ask. Just watch the videos, just listen. I'm trying to put the information in story form, so that way it's easier to comprehend. I'm also not going a whole 50 minutes, because longer, I know in these kind of settings, at least to me, I'm like, I'd rather them learn kind of a lesson of the day and not overwhelm them with too much stuff, or it gets boring or monotonous. So today's lecture is going to be focusing on movement strategies with the concept of power. So once again, concepts of continuums, right? We'll talk about continuums. There's a lot of different continuums. You learned about joint types and continuums. In phys, you learned about muscle fiber types, right? Fast twitch, slow twitch, but there's a continuum. One of my physiology professors used to say there's technically as many different fiber types as there are motor units, meaning that every motor unit and all of the fibers that they innervate are somewhat different. There may be similar, but they're never going to be perfectly the same. So with these movement strategies, we're also in this continuum. Extreme, and then what lives kind of in the middle, and everything falls on that continuum. Last lecture, I talked to you guys about simultaneous movement strategies, the canceling out of motion, so that you can have accuracy and or strength. Again, if you're trying to push someone and impart optimal, maximum influence on them, you want to be accurate in your delivery. In other words, elbow and shoulder moving at the same time, so that the elbow doesn't take it up here, the shoulder doesn't take it out here. Application of a push. Remember, muscles don't push, but your hands can push, bones can push. The application of that push is going to be dependent on the accuracy of the delivery of that push. So force and accuracy kind of go hand in hand. Another thing from reminder of last lecture, you can be accurate without necessarily having a ton of force, but you can't apply a big amount of force onto something and not have the intent of being accurate. And that's because force is a vector quantity. Remember from high school physics or college physics, you should have physics before this class. Force is magnitude and direction, meaning magnitude, how much, and direction. So that's where the accuracy comes from, the direction of that influence, the direction of that force matters in terms of its delivery. So accuracy and force go hand in hand, especially when you're trying to import something large on something else. I want to say before I continue, if you are genuinely watching this video, today I want you to comment confirming that you watched it with the word done. It's your secret word of the day. Comment done instead of watched it. Just kind of want to see who's actually made it to 4 minutes and 15 seconds. So done, comment done. All right, so in physics, I told you guys last class that work, the terms work, involves movement, right? And remember in 310, I said even with isometrics, that's work, because even though there's no mechanical movement in terms of joint motion, there's physiological work going on within the muscle. In other words, there's movement going on in there within the muscle in order to prevent that motion from happening. So physiologically it's working. Work is force and distance. Force times distance, and distance is relative. Are you talking about up, down, front, back? And if it's a combination, you got to, how much work did you do here? How much work did you do here? Okay, force and distance. And force, as we know, again, scalar quantity. So work has this element of simultaneity to it, simultaneous motion. When you're trying to do work on something in a straight line, you're going to impart accurate force, efficient delivery of that influence. And when you actually move something, that's what we consider mechanical work. However, on the other end, right, how much time did it take you to do the work? And once we impart time, then we have this element of speed. I'll give you an example of how time can be inferred to speed, or where we assume, I hate using that word, assume. 40-yard dashes, right? We know that it's a test of speed, but yet we talk about it in terms of time. And the reason we can do that is because we know that everybody is working the same, everybody's displacing the same, everybody has the same change in distance, right? Displacement, if we're talking about direction. But the point is that everybody's work, everybody's distance. Now, they may have variations in force, and thus force times distance, but my point is that the top part is the same for everybody in terms of distance. How much time it takes you to change, how much time it takes you to displace, that's what infers velocity. So in other words, if we all know that 10 people ran 40 yards, but one of them ran it in less time, we can infer that they had to be moving faster. It's almost like a proof. If we covered the same amount of ground, but you covered it in less time, you had to be going faster. So we infer velocity. So time is a speed factor because we infer speed because it's relative to time. And that's what the definition of velocity is. It's displacement over time. Speed is distance over time. In other words, that element of time infers speed. Okay? So we have the top part that infers force and accuracy. We have the bottom part that infers speed. So my point is that what do you get when you combine force and accuracy with a time element? And that's what power is. Power is work in regard to time. How much time does it take you to do the work? So if two people are moving bricks, stack of bricks, and they move the exact same bricks and they put them in the same place from here to there, we can infer that the person who did all that work in less time would be more powerful, assuming they were going as fast as they can. So we try to keep, the intensity the same. In powerlifting, there are some movements that require, even though we're not timing for speed, it behooves you to make that heavy weight go fast. Meaning that, let's say, for a clean or for a clean and jerk, the faster you get it moving up, the more time it's going to stay in the air, and the more time you get to lower yourself underneath it to catch it. If you did that movement real slow, imagine that. If you did it real slow, if you did that movement in more time, it would be harder to go up underneath it, right? So again, time can sometimes be inferred. But power means, in movement strategies, you're moving something somewhat heavy or heavier than one joint can do on its own, but you're trying to make it go as fast as possible. So let's do a couple examples of the different movement strategies, okay? First one, a sequence, and everything's going to be using a ball example, and I'll try to pull up some photos on my phone, and let's see if it translates to medicine ball. Let's see if you can see it on the screen. Okay. Let's see. Everybody see that medicine ball? Look at medicine ball. So we can have two extremes. Let's say we have a baseball. Now, what do we know about a baseball? Some professionals can throw it real fast, but it doesn't weigh very much. So the fact that it doesn't weigh very much, there's not a lot of mass to it, that means that my sequenced motion, movement strategy that lends to maximum velocity of the distal segment, but every joint has to work one joint at a time, right? So that means every joint has to be able to handle the weight. Every joint has to be able to handle those forces, because I'm doing trunk, then I'm doing scapula, then I'm doing shoulder, then I'm doing elbow, then I'm doing wrist. So when it comes your joint's turn in the sequence, it has to be able to handle all of that force. And remember, it's not just the force of the baseball. You're getting some inertia, some resistance when you're talking about whipping something. You would not, let me get this photo up here, you would not throw, if I asked you, check this out. So if I asked you to take a shot put, okay? So let's look at this shot putter. It's a heavy ball, right? A lot more dense, a lot more mass than the baseball. You would not take a heavy shot put and have the exact same movement strategy as a baseball. And you couldn't, because you imagine if you tried to do this with your shoulder, right, that just doesn't sound very safe. It would hurt. It's too heavy for each individual joint to handle one at a time. So if the concept is, let's say my 10-year-old son, if I took an Olympic shot put and I said, hey, Brian, lift it up. And the goal is just to move it. When you just move something and there's no time component, that's work, force, accuracy, just move it. So he might have to get underneath the ball or the shot put on the ground and literally use his whole body to get it up. Simultaneous motion of his legs, maybe some simultaneous motion with his trunk, but maybe his little arms, bless his heart, can't handle all that force, even though they could be moving simultaneously. The young kid, he doesn't have much muscle mass out there. Too many video games. So for him, simultaneous motion, because it weighs too much. He needs force and accuracy to lift it up. Now, imagine someone like us, and the goal is throw the shot put as far as you can, okay? Because that's how the shot put works, right? You're taking something heavy and you're trying to make it go as far as you can. The faster, this is where speed can again get inferred. And this is why it's commonplace to play fast and loose with terms, because we have so much inference of these defined biomechanical terms. To make something go as far as you can is another way of saying I need to make something go as fast as I can. Because if you think about it, the faster it leaves my hand at the same angle, let's infer that we give the same angle of release, the faster it leaves my hand, the more time it's going to spend in the air. Well, that's angles. The faster it leaves my hand, no, that's true. The faster, if let's say I angle it at 45 degrees, the faster it leaves my hand, the more time it's going to spend in the air, because it's going to take more time to slow down as it goes up, and it's going to take more time to speed up as it comes down. In other words, if I leave the shot put with just a little velocity, it's not going to go as high, it's going to fall sooner. To make it go further, I have to make it go faster. So throwing the shot put, herein lies a not a conundrum, but a movement strategy. We need force and accuracy because that darn shot put is heavier than a baseball. But we have the element of speed because we're trying to make it go as fast as possible. Just like throwing a baseball. If you're trying to throw a fastball as fast as you can, you're trying to make it go as fast as possible. The only difference is that the shot put weighs a heck of a lot more than the baseball. So a movement strategy that takes something heavier and tries to move it as fast as possible requires a blending of those two extremes. A powerful movement strategy. And powerful movement strategies take elements of both. Follow me here. Our lower extremity, knees, hips, and ankles, simultaneous motion of the lower extremity can handle the weight of the shot put. And for most adults, simultaneous motion, maybe not my little son, but simultaneous motion can handle the weight of the shot put in my upper extremity. So I want you to think about this as two tiers of simultaneous motion, two tiers of hydraulic lifts. We have a hydraulic lift in our upper extremity, and we have a hydraulic lift in our lower extremity. The whole trick about trying to speed something up is giving it time to speed up. So in other words, if you're trying to speed up a merry-go-round with kids on it, right? Let's say it's recess and you're playing with the kids. The more time you spend pushing the merry-go-round, the faster and faster and faster it's going to go. So time is an element. Actually, that's acceleration, because speeding up in regard to time. How much time to speed up, okay? So my point is that it should make sense that the more time I spend speeding up the shot put, the faster it's going to go when it leaves my hand. So let's think about how I can strategize to speed up the shot put. I can have a sequence, things done in order, where I can, if I'm lowering on the ground, I can go up with my lower extremity, right? I can speed the shot put up by extending my knees and extending my hips. But if you notice, while I'm doing this with my lower extremity, I haven't moved any of my upper extremity. It's prepped. In biomechanics, a common term is prep phase, action phase, and then follow-through phase. Follow-through is just basically what it looks like after you do your action. But if my lower extremity is actually speeding up the shot put, which it is, my upper extremity is prepped. It's being put in a position because it needs to wait its turn to continue speeding up the shot put. So again, something heavy that I'm trying to move as fast as possible. I'm going to use a sequence of simultaneous motions. I'm going to go upper extremity first, and then after I speed it up with lower extremity first, then after I extend my hips and extend my knees, I'm going to immediately continue on that acceleration, that speed up, with simultaneous motion of shoulder, elbow, and scapula. Lower extremity simultaneous, followed by upper extremity simultaneous motions, lower and upper, done in sequence. And then you can look at it even further. Some like top level shot putters, like they speed it up by shuffling first. Some of them spin around. It's all part of a sequence. So if you slide step, that's speeding up the shot put first. Then you twist, that continues the speed up of the shot put. Then you lower, then you upper. All of those things done in sequence. Sequence, speed. but the simultaneousness of the individual segments of that sequence because it's heavy. Okay? So another classic example of just straight up power, vertical jump, right? So yes, a majority of you speeding up, going up in the air, our action phase is going to be knees and hips in simultaneous motion. But think about what happens before. You start swinging your arms up and your back starts to extend before you trigger your lower extremity. That's part of a sequence. You fall down and then you do this and then the legs go up. And then after you extend your hips and your knees, then your ankles continue to plantar flex after. That's part of a sequence. So vertical jump is a powerful movement because it's going to have elements of both. It's going to have some force and accuracy through simultaneous motion, and it's going to have sequenced motions to add an element of time or speed. Time. The more time I can spend speeding up, the faster I'm going to go at the end, okay? Let me try to give you another example. Let's see, we did the vertical jump, running, sprinting specifically. So let's think of how sprinting can be powerful. Now, remember, I'm looking at it as a biomechanism from the movement strategies. Physiologists can look at power from the fiber types and the speed and force and that kind of stuff. I'm just looking at it in terms of biomechanisms for movement strategy. So think about what is heavy. You are heavy. You are significantly massive. More than this, right? And think about what the function of sprinting is. Trying to move fast. So the weight is you, and the task is speed. Make you go fast. So let's talk about how that could be considered powerful. First is, what are my simultaneous motions and why do I have them? Well, when you're sprinting, you're going to have right arm moving at the same time as left leg. That's simultaneous. Left arm, right leg. Right arm, left leg. Now let's talk about what that simultaneous motion would do. First of all, from an accuracy standpoint, they would cancel out, meaning that my right arm is trying to swing my trunk over to its left, but my left leg is trying to swing my pelvis over to the right. So they cancel out and allow me to go straight. Think about it. When you're sprinting, direction matters. Because if you're doing a 100 meters and you're drifting over, you just wasted distance, right? It's about how fast did you go in a specific direction. So being accurate is a part of sprinting. If you're playing tag, being accurate is a part of sprinting. Sprinting where I want to be able to sprint. And one of the ways you're accurate is by canceling out motion. Now, another thing that's happening cool too, this is kind of like right then left, left then right, cancel out motion, allows you to kind of go straight, more accurate. But another thing that's happening too is kind of some action-reaction stuff of force. When I swing my right arm and my left leg up, the reaction of that is my leg pushes harder down. Think of it like this. If you were, see our little mantle here? If I'm sitting under it, let's look at it like this. If I'm sitting under it and I push up on it, I'm going to push harder into my seat. Does that make sense? If I push harder on the mantle, the reaction of that is going to be me pushing harder on the seat. So the same thing happens. It's not that extreme because I don't have anything solid. But when I swing my arm and my leg up, the reaction to that is my foot pushes harder down. Force and accuracy because of simultaneous motion. Okay? Now where's the sequence? The sequence is rights and lefts alternating back and forth. That's where the speed comes from. So in other words, right arm, left leg, followed by left arm, right leg, followed by right arm, left leg, followed by left arm, right leg. That's where the speed comes from, the sequence of those simultaneous motions. Simultaneous motions done in sequence. Power. So sprinting is a very powerful movement because it has some elements of both simultaneous motion and sequenced motion, okay? Your homework, practice these concepts so that you can make an A on the test, is think about some extreme motions in areas of your interest. If you're crossfitting, what are some movements that could be more pure simultaneous? Remember the intent of simultaneous, man. You're lifting something very heavy. It doesn't matter how much time it takes, or there's no indirect need to make it move fast, like to get up underneath it real quick. Weightlifters, what are some, or if you work at the gym, or if you want to be a fitness professional, think of some exercises in the gym that are simultaneous in nature. And remember, it doesn't mean it has to be heavy. I can get on a bench machine and put light weight and still have simultaneous motion. Accuracy, okay, so it doesn't have to be max. Then think about, or you people, coaches, think about sports that you have interest in: basketball, baseball, volleyball, track and field. Think of some things in your field that have simultaneous movement strategies and then have sequenced movement strategies. Stuff on this end of the spectrum, stuff on that end of the spectrum. And then try to blend them together and think about power. Okay? Now again, sequence, man, it's hard to be pure sequence. That takes a lot of learning. And so again, people who are doing things for the first time, novices, young kids who don't have a lot of muscles yet, muscle tone to do, they may take more simultaneous strategies, or they may take more powerful strategies for these sequence motions, because they have to, until they learn or adapt or develop where it could be more sequence. Okay, so again, think about someone who, again, I love the shot put analogy, because you can't take a shot put and throw it like you would a baseball. So how do you throw a shot put? You have to have a different strategy in order to make something heavy go fast. Okay, so that's your lecture for today. Don't forget to comment done in the comments below, D-O-N-E. Reminder, guys, I'm trying to make these videos 30 minutes or less, little bites of the apple. I figured that you'll have a better chance of remembering it, learning it, not overwhelming you with boring at-home videos. So I hope everybody has a good Monday. I'll see you on Wednesday. Oh, reminder, you have until the night before the next lecture to watch it. So in other words, this lecture on Monday, you have until Tuesday at 10. Wednesday's lecture, you have till Friday at 10. Thursday at 10. Monday's lecture, Tuesday at 10. Wednesday's lecture, Thursday at 10. Friday's lecture, Sunday at 10. All right, guys. Y'all be well.